Hi, my name is Bishal Adhikari. I'm currently a PhD student at the School of Pharmacy, University of Otago. This presentation is on the potential use of co-amorphization as a strategy to prepare stable high-dose amorphous antibiotic dry powder using a spray dryer to treat lung infections. High-dose dry powder antibiotic inhalation is becoming a standard in the treatment of bacterial infection in different pathophysiological conditions, such as cystic fibrosis. Among the different techniques which have been explored to prepare high-dose dry powder, such as direct crystallization, milling, supercritical fluid techniques, etc. Spray drying is emerging as a promising technique, particularly because of its ease to modulate both particle size and morphology. In addition, reproducibility and scalability are its other advantages. Upon spray drying, the drug or excipient can precipitate in crystalline or amorphous state. Its solid state form has its own advantages. For example, crystalline solids are thermodynamically stable and are usually preferred. However, as the spray drying process involves a rapid precipitation, in many cases amorphous particles are formed. This can hinder product development as such solids have poor physical and chemical stability as well as poor aerosol performance. So in the next slides, I'm going to talk a little about improving stability as well as aerosol performance of such amorphous solids. Physical stabilization of amorphous solids revolves around two strategies. First, controlling the environment which can induce crystallization. For example, samples can be stored at low temperature or protected with appropriate packaging from moisture. Second strategy involves limiting molecular mobility of the molecules. This can be achieved by different techniques such as solid dispersion or co-amorphous systems. A solid dispersion refers to the technique in which a drug is dispersed in a matrix of polymer so that the amorphous state becomes kinetically stable. However, the major drawback is that it will dramatically increase the dosage volume as drug loading is quite low. On the other hand, co-amorphous system refers to amorphous matrix in which the drug forms a homogeneous single-phase molecular mix with another drug or small molecules such as amino acids or citric acid. It can be thought of as an equivalent to co-crystal for crystalline systems. Such matrices have been proven to be physically stable. Similar to physical stability, chemical stability can also be improved with such techniques which reduce molecular mobility or moisture content. Next, looking at techniques to improve aerosolization. Use of excipients is a common effective technique. Among various excipients, leucine and amino acid is a proven aerosolization enhancer, and the mechanism of its effectiveness has been ascribed mainly to its ability to introduce surface asperities. This asperities can improve deagglomeration process by decreasing cohesive van der Waals force by reducing effective distance between the particles. In addition, they can improve the aerodynamic behavior. Another amino acid which has similar features in terms of polarity, hydrophobicity, and molar volume is valine. However, this molecule has not been much explored. So the aim of the work was to assess the influence of co-amorphization of valine with a drug on its aerosolization and chemical stability. So ceftazidime was used as a model drug. Ceftazidime is a cephalosporin class antibiotic which is potent against Pseudomonas aeruginosa, a common pathogen causing lung infections. Here, two different spray dried formulations were prepared. The first drug was drug only ceftazidime or C, and the other with valine, ceftazidime valine or CEV. The amino acid was used in 1:1 molar ratio with ceftazidime, and a feed concentration of 0.2% weight by volume was used in both the cases. Following production, a complete characterization was done using different spectroscopic as well as thermal techniques. In addition, chemical stability was assessed at the end of 10 weeks in low humidity condition at 25 degrees Celsius. The fine particle dose, representing total particles with aerodynamic diameter less than or equal to 5 microns, was calculated by interpolation of graph plotting cumulative mass deposited in different stages versus the d50 of the stages, and the fine particle fraction was expressed relative to the recovered dose. Coming to the results, the XRD with characteristic amorphous halos without any peaks suggested that the ceftazidime only and ceftazidime valine formulations were amorphous. Valine was crystalline upon spray drying alone. However, it was amorphous when it was spray dried with ceftazidime. The water content in both the formulations were around 5%. So the XRD suggests that the ceftazidime valine formulation is amorphous. However, the technique doesn't provide information regarding phase in the matrix, and hence modulated DAC was used to assess if the ceftazidime valine amorphous matrix was monophasic or biphasic. Co-amorphous system would show a single glass transition as shown in the diagram, and so a single TZ at around 50 degrees Celsius suggests that the ceftazidime valine formulation was a co-amorphous system. Now looking at the aerosolization, we can see that the use of valine improved the fine particle fraction, or the FPF. Both formulations had similar particle size of around 1 microns. The particles of ceftazidime only formulations were spherical without any surface roughness, as you can see in the figures. However, ceftazidime valine particles showed surface roughness, which potentially contributed to better fine particle fraction by a cohesive force decrease between the particles by reducing effective distance between the particles. During the chemical stability study, the formulations were kept in a low humidity of less than 15% at 25 degrees Celsius for 10 weeks, and the drug content were assessed at the end of the 10 weeks using HPLC. A lower chemical degradation was observed in the formulations with valine. In total, 24% reduction in chemical degradation was observed with the use of valine. So different works have shown that non-covalent interaction between a drug and excipient can potentially improve chemical stability. Here, the interaction between valine and ceftazidime could not be evaluated using FTIR, as we were unable to obtain pure amorphous valine. However, similar behavior was observed with ceftazidime and another amino acid, and molecular interaction was identified between the amino acid and ceftazidime in the system. Hence, in this system as well, valine potentially interacts with ceftazidime and reduces its chemical reactivity. All in all, this study suggests that co-amorphization with valine can be used to formulate high-dose amorphous dry powder with improved aerosolization and chemical stability. I would like to thank my supervisors, Associate Professor Samuel Das and Professor Keith Gordon, for their support and guidance. Also, I would like to thank the University of Otago Research Grant for funding this work. In addition, I would like to thank the University of Otago for the doctoral scholarship and School of Pharmacy and Chemistry for the facilities. Thank you for listening, and please do feel free to email me if you would like to discuss on this.